we have actually both this equipment, spectrum analyzer and radar, in our lab, and we used to demonstrate them face to face. However, this time we are managing somehow this demonstration. For spectrum analyzer, we will use a video just downloaded from YouTube. And it's a handy equipment, so this demonstration can probably explain its use very well. And for the radar, we actually captured a video running it in our lab, and we'll demonstrate them. These videos I have already uploaded. However, a part of these videos, while I was uploading, failed. I mean, I will upload that again. I'll try it again after this class. So inshallah, by evening we'll get all the videos available. And for radar, I have also uploaded a quick lab sheet, a short lab sheet. Okay. So let's demonstrate the spectrum analyzer first. So I will run the video demo, and if you have any questions, you can just interrupt. Okay.
Sir, yes, sir, your network is, I think, a little unstable, sir.
Oh, really? Then I should switch to my alternative. Give me a second. Okay, I'm now using a different connection. Okay, I'll now share the video. If you cannot listen to the sound from the video, please let me know. Do you hear the sound from the video?
No, sir.
No.
We can just see it.
Okay. So I think, give me a second. There is an option. Uh,
স্যার শেয়ার স্ক্রিন করার সময় নিচে কি ওই যে শেয়ার সাউন্ড
right, right. Yeah. Thank you for the reminder.
Spectrum analyzers are one of the key pieces of test equipment for RF design and test. The oscilloscope we're all very familiar with displays the instantaneous voltage on the vertical axis against time on the horizontal axis. This shows waveforms in the time domain. But the spectrum analyzer is different. It displays waveforms in the frequency domain, displaying the amplitude in the vertical axis and frequency on the horizontal axis. It's like tuning a traditional radio receiver over a band of frequencies and marking the points where the signals occur.
Excuse me, do you hear me now? You don't, right?
Yes, sir. We hear the video,
We can
sir.
hear you, sir.
I mean,
Hear the video,
you
sir.
can hear me too, right? When I
Yes,
speak?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir. Now it's okay,
So-
sir. Yes.
Okay, so from time to time, if I need, I'll say something like, I mean, it's just a display of power versus frequency. Okay, you may capture the signal from the air. In our test equipment, we connect an antenna. So this, I mean, it just captures whatever signal you have in the air. So it shows power versus at different frequencies. You know that using Fourier transform, we can just show the components at different frequencies. So it shows what power level you have. Okay, I mean the amplitude or whatever is shown here actually relates to the power level. Okay. So, but you also have some noise. Okay, both generated from the equipment and from different sources.
So in the physical lab, sir, would you have showed us this video or the real equipment? Is it available, sir?
The real equipment every year we used to show.
Okay, sir.
Okay,
Okay, sir. Okay, sir.
definitely. I mean, both the demonstrations today, both the video demonstration will be just alternative solutions to what we used to do in our lab classes.
Okay, sir. Okay.
Okay. Even the last year we did that. We did that before we had done them before the lockdown started.
Okay, sir.
Except that the spectrum analyzer indicates the amplitude of all the signals with a high degree of accuracy. Spectrum analyzers are manufactured by a number of companies and they come in a variety of formats. Some are contained in traditional cases which can be mounted in 19-inch racks, whilst others are more suitable for portable operation. Some may be incorporated into systems like PXI racks. Others are designed to be used directly with computers, often connected via USB links, enabling the computer's processing power to be used. Each format has its own advantages and disadvantages, and a choice has to be made for each application. Despite the differences in the way they are presented, spectrum analyzers follow the same basic principles and their operation follows the same basic rules. Here we see a typical spectrum analyzer once it's been turned on. The most pronounced feature of what we see here is the display. Other features on the front panel include the soft keys around the display itself for some of the functions, but the more important controls are contained on the keypad, which is used for the main functions including the entry of figures for frequencies, span widths and the like. One of the first items to be entered into the analyzer is the center frequency. The center frequency is used because the wanted signal can then be seen at the center of the display and other signals either side of it. Once the center frequency has been set, the span can then be entered. The span is the width of the frequency band that is displayed. As the span is reduced, so too the background noise level falls, and also signals closer into the wanted one can be seen more easily. It'll usually be necessary to adjust the level controls. The reference level can be changed so that more of the signal of interest is seen on the display. Some older analyzers had separate controls for RF and IF gain. These days, modern analyzers combine the two intelligently, so that it's just a matter of adjusting the reference level to place the signal with the peak towards the top of the display as shown. If you reduce the reference level too much, then the signal starts to disappear into the noise, so it's important to get it into the right region. Typically, a minimum figure of 20 dBs between the signal and noise is required for good measurements. Much closer to the noise, and the signal level will be seen to vary because the noise level is sufficient to add to the signal and affect the overall result. Here we see an amplitude modulated signal on the analyzer screen. But in order to see the...
By the way, give me a second. You all can hear me, right? You can hear me, right, guys?
Yes, sir.
Yeah, okay. So you need to set, you can use the soft keys, okay, next to the display. So, and as it already mentioned that the keys in the keypad helps more actually. So anyway, you set the center frequency and then the span over which you wanna see. Okay, so like if you want to see from 2 gigahertz to 2.5 gigahertz, okay, or maybe say 3 gigahertz. So then the center frequency will be 2.5 gigahertz. Then the bandwidth or the span, okay, will be 1 gigahertz. So around the center frequency, it will show the variations, okay, power versus frequency over the whole span. Okay, let's get back to the demo.
sidebands, we need to adjust the span. As this is progressively reduced, the spectrum analyzer scans a smaller bandwidth and the sidebands are seen. In reducing the span, the analyzer has two controls linked together. The first and most obvious is the span, the actual band that has been scanned. However, it also reduced the resolution bandwidth. This is the same as the reception bandwidth of a radio. The smaller the resolution bandwidth is, then the higher the resolution of the scan, the more detail there is. The downside to a narrow resolution bandwidth is that the scan takes longer to perform. As a result, a spectrum analyzer links narrower resolution bandwidths to the smaller overall scan widths, otherwise they just take too long. The noise level also falls for lower resolution bandwidths because the noise is proportional to the bandwidth. This means it's easier to see lower level signals because they're not masked out by the noise. Taking the resolution bandwidth on its own back up, it's possible to see that the detail is lost. For modern spectrum analyzers, the resolution bandwidth...
I think I need to explain this part. Resolution bandwidth, RBW, and span. Okay, we already discussed what the span is. It is the whole range of the frequency that you have on the display. Okay, so as you reduce this span, of course you have a better resolution within your display, right? If you have a long span, then the whole variations will have to fit in your display. So by resolution, I mean how well you can separate two points in frequencies. I mean, if you can separate the power levels at closer frequency points, then your resolution is better. Okay, so how close frequency points you can identify, or you can properly separate their amplitude levels. The amplitude levels are varying, but how well you can actually recognize the separation in the amplitude levels at close frequency points. So this is the quality of resolution. So as you reduce the whole span, you have better resolution. Another point for another way to improve the resolution is setting RBW. So there is a control by which you define the RBW. You may set it say 3 kilohertz or 30 kilohertz or even higher. Okay, so you set some value for your RBW. what that is. RBW is like a, well, the way it works, it uses the superheterodyne principle. So you actually, for the whole span, one of them, like if your whole span on the display is 300 kilohertz and your RBW is 3 kilohertz, then what it will do, using superheterodyne principle, it will check the power level for every 3 kilohertz. For, I mean, the bandpass filter that you have for after IF amplifier, you know, there is a bandpass filter. That filter will be 3 kilohertz wide when you set RBW 3 kilohertz. So then you, for this small bandwidth, 3 kilohertz, you check how much power you have and then put a dot, okay, on the display. For the next 3 kilohertz, again, you determine how much the power level is. And accordingly, you set a dot or indication on the display. For every 3 kilohertz, you are performing the power level detection. And accordingly, you will create the whole profile on the display for the, you know, I mean, it will take 100 times to complete the whole span of 300 kilohertz. Now, if you increase this RBW to 30 kilohertz, what will happen? You can actually complete the whole scanning of 300 kilohertz span in 10 steps. 30 kilohertz, again 30 kilohertz. So 10 steps will complete the whole scanning. But for the power level detection, your resolution is now wider. For over 30 kilohertz, you are determining how much the average power level is over this whole frequencies, how much the average power level is. So the granularity in the frequency domain is now poorer. For every 30 kilohertz, you get an estimation of the power levels. Previously, for every 3 kilohertz you had. So you are then able to separate if there is, if there is significant difference in the power level between 2-3 kilohertz components. You can find out when you set the RBW to 3 kilohertz, but with 30 kilohertz, they all will just merge. Okay, you cannot separate between 2-3 kilohertz components, or your granularity is now poorer. The resolution that you work with is now poorer. So the advantage with our lower RBW is a more precise detection of power level variation with frequencies, okay? Better granularity or resolution you have. On the other hand, the disadvantage is that it takes longer to complete the whole span, okay? This is called sweep time. How long it takes to complete the scanning of the whole span. If your sweep time, so I mean, with smaller RBW, your sweep time will be then longer. The problem with the long sweep time is that you actually update after you complete the whole 300 kilohertz, then you again start from the beginning. In another sweep time period, you complete the whole scanning. Okay, but the power levels may be changing. Okay, so you are updating your display less frequently. In the time domain, it may be changing too fast, but you may not be able to trace the fast changes. Okay, when you have smaller RBW. So when you have fast changes and you want to trace the fast variation, then longer RBW may help you. But when in frequency domain, you want to be more precise, then smaller RBW is more helpful. Okay, so see a while ago, the RBW was lower, so it could separate the power levels at these different resolution bandwidths, at these different frequency chunks. But when you reduce when you increase the RBW, okay, you actually, I mean, things get sort of merged. You cannot separate that well, right? So I mean, before that we had longer span. Also, I mean, just reducing the span, you could find out the separation.
Reduced, the spectrum analyzer scans a smaller bandwidth and the sidebands are seen.
Okay, so as you reduce the span, you can then see that, okay, actually there were three different I mean, frequency power level jumps. Okay, in fact, in modulation, I mean, carrier with sidebands, you should have like I mean, some display like this. So they can be identified. So when you reduce the span, just by reducing the span,
Signal on the
you can
analyzer
separate.
screen. But in order to see
You
the
can-
sidebands, we need to
can-
adjust the span. As this is progressively reduced, the spectrum analyzer scans a smaller bandwidth and the sidebands are seen.
Mhm.
In reducing the span, the analyzer has two controls linked together. The first and most obvious is the span, the actual band that has been scanned. However, it also reduced the resolution bandwidth. This is the same as the reception bandwidth of a radio.
I mean, when you reduce the span, the resolution band, I mean, you actually have a separate control. When you reduce the span, you'd have, I mean, on the display, you'd see the resolution bandwidth it shows. You'll see that automatically that also reduces, but you can actually separately control the RBW. You can separately set a value. Okay.
The smaller the resolution bandwidth is, then the higher the resolution of the scan, the more detail there is. The downside to a narrow resolution bandwidth is that the scan takes longer to perform. As a result, a spectrum analyzer links narrower resolution bandwidths to the smaller overall scan widths, otherwise they just take too long. The noise level also falls for lower resolution bandwidths because the noise is proportional to the bandwidth. This means it's easier to see lower level signals because they're not masked out by the noise. Taking the resolution bandwidth on its own back up, it's possible to see that the detail is lost. For modern spectrum analyzers, the resolution bandwidth is normally automatically chosen to provide the optimum resolution for any given case.
And the point they probably mentioned, when you reduce the resolution bandwidth, the noise also lowers. Why is it so? You are actually taking over, I mean, from the bandpass filter, you are capturing over a smaller bandwidth. Now you have some noise everywhere. You have noise everywhere at all frequencies. So when you capture over a small part, you get noise only from that small range part of the frequency. The small frequency chunk has lower noise, right? Say over 10 megahertz, you have the total noise has certain value. I mean, noise multiplied by, I mean, noise per frequency per hertz, okay, has certain value. So when you multiply by the bandwidth, you get how much noise power you have over that bandwidth. So with smaller resolution bandwidth, you are capturing over smaller chunks. Okay, you are taking the always over smaller chunks. So for every collection, you have lower noise. So the overall noise is will be better, and that is important for spectrum analysis because there are already a lot of noises, okay, from different sources. So it is very sometimes it gets difficult to separate your actual desired profile from the noises. Okay, so anyway.
A very useful capability of modern analyzers is the ability to add markers that show the parameters of a signal at a particular point on the screen. The most obvious one is a marker for the highest level signal. The marker shows the major parameters like frequency and
It will
Cool,
itself.
sir.
Sorry, what is the question? Any question?
Yes, sir. There was a little latency and then everything became fast forward. Can you like go like 10 seconds behind and play again, sir? Kindly. We couldn't hear anything, sir.
Oh, because of poor internet?
Sir, like there's a latency, sir. I think there was some packet loss. in the processor.
Okay.
Just like if you could just has, I think it's the internet, sir. It's raining
Okay.
outside, so like it's
Okay.
over obvious.
Well, but if you try to watch the video later, probably
Yes, sir, we could
you
also
can
do that. Yes, sir.
make up
Okay,
whatever
okay,
we are losing. We are already sharing everything in our Google Drive.
okay, okay, sir. Okay.
And you see now you see that it itself can capture the maximum frequency. When you peak search, there is a button peak search. When you use that, it will show you where you have the maximum level of frequency. It will give both the amplitude and the frequency. Okay.
Amplitude. Normally, it'll automatically find the peak of the signal. Another popular marker is known as a delta marker. This typically takes the second highest peak, giving the frequency and amplitude, as well as the offset from the main marker, typically in amplitude and possibly frequency. This is very useful for determining the attenuation of spurious emissions relative to the wanted signal. Some analyzers have screens that show other marker capabilities. These will vary from one analyzer to the next, but this one shows aspects like phase noise, decibels down on the carrier, as well as a host of other features. With spectrum analyzers relying heavily these days on processing technology, they often contain many inbuilt routines. These cover many functions, everything from channel power to harmonic distortion, and third-order intercept to AM modulation measurements. Two routines that deserve special mention are phase noise and spectral emission masks. Phase noise is a critical parameter of many oscillators and systems. High levels of this noise can cause many issues. Unfortunately, all signals have some level of phase noise on them, as can be seen here. It can be difficult to measure phase noise accurately, but many analyzers these days normally have an inbuilt routine to do this. It notes the carrier frequency and then scans out from the signal using narrow resolution bandwidths so that it can capture the close-in phase noise. As the scan moves further out, the resolution bandwidth will increase, but the routine will normalize for this. The standard for these measurements is to measure noise in a 1 Hz bandwidth relative to the carrier, and measurements are expressed in the form so many dBc per Hertz at a given offset from the carrier. In this measurement, it can be seen that the result is minus 140.
Many spectrum analyzer, I have experience with quite a few. Actually, it does not have this capability to show you this phase noise measurement. So I think we can skip. I mean, you may. I mean, it is good that you learn this part. I mean, I'll play from here, but we'll skip this phase noise measurement part from our syllabus for the quiz. Okay, I mean, there will be a quiz. Okay, we won't use this part. Okay, we'll skip this part for our for any testing. Okay, and ours. Okay, the equipment we have in our lab cannot measure this phase noise.
0.63 dBc per Hertz at a 10 kHz offset from the carrier. This screen shows a typical plot for phase noise. It can be seen to be reducing as the offset from the carrier increases. One important point to note is that on a spectrum analyzer, the phase noise is measured against the analyzer local oscillator. Any noise on this oscillator will be superimposed on the plot. Therefore, the oscillator should have a noise performance better than the signal being measured by about 10 dBs. Other techniques like cross-correlation are present in phase noise measuring systems, and this overcomes the issue. But these systems are normally very specialized and much more expensive. Spectral masks are very useful for seeing whether a signal and its spurious emissions fall within acceptable limits. The mask sets out the maximum levels at a given point. For this example, the signal in yellow can be seen, and the mask can just be seen in red. As the signal falls within the red outline, it passes this test. A more complicated example can be seen here with a wideband CDMA signal, and the test is ensuring that the level of spurious signals in adjacent channels falls below the accepted levels defined by the mask. Although analyzer performance levels these days are very good, it is still possible for the input to become overloaded. When this occurs, spurious signals can be generated within the unit itself. This can be an issue because it may not be obvious whether these signals are generated by the item under test or within the analyzer. It's easy to check this. To see how this can be done, we're looking here at two tones with some additional intermodulation products that are lower in level. These could come from the unit under test or the analyzer. This can be checked by changing the input attenuation, and it can be seen in this case that the relative levels remain the same. This means that they are present at the input of the analyzer and not generated by the test equipment. Spectrum analyzers are complicated instruments to use, so we talked to some industry experts to find their top tips for using them.
Detectors and traces on the spectrum.
Instruments to use, so we talked to some industry experts to find their top tips for using them.
My top tip is in relation to averaging. You have many different types of detectors and traces on a spectrum analyzer. Some of them are logarithmic, some of them are linear. Make sure you understand the difference between the two.
Make sure that the spectrum options match your application requirements.
I would advise to look a little bit beyond the traditional RF specifications like spurious free dynamic range or third order intermod, and look at the capabilities requiring discovering transient signals, triggering on them, capturing them, and then doing multiple lane analysis.
My top tip would be to ensure that you have all the latest software and firmware upgrades on your instruments to ensure that you're picking up all of the latest facilities that are available, possibly for free.
Okay, I need to add just one feature to the demonstration, and that is video bandwidth. Okay, we spoke of RBW, resolution bandwidth, and I will add video bandwidth, which is called VBW. This is also something you can set on the equipment, and it is like a final filtering of the signal to smooth out. Okay, so before the display, how well you smooth out your signal, and a lower VBW is better capable of showing your signal level compared to noise. Okay, I mean you find lower noise in the display as you have smaller bandwidth, but again, if you work with this better or more precise determination, better precise detection, then it takes longer. So as you lower your VBW, again sweep time increases. So that's the disadvantage. Okay, but the overall noise that you have will be lower. So I said that in the case of spectrum analysis, a lot of times you have to struggle which one the real input signal is, your desired signal. Okay, or maybe you can connect using cable. You can feed the signal using a cable, or you can connect an antenna. Okay, so you have something on test, and from there you are taking the signal and feeding it to the spectrum analyzer. So however you do, how well you can separate your actual desired measurement item have some signal which may get confused with the noise. Okay, so VBW, lowering VBW may help you this way. So we have both sweep time. Sweep time is inversely proportional to RBW, and it is also inversely proportional to VBW, or you can say if you multiply RBW and VBW, okay, this product is inversely proportional with sweep time. Okay. Questions? Okay, if
No,
okay, then let us move to our next presentation. It is radar. Uh, with radar, you can detect objects around. Uh, the way it works, it sends some signal using a transmitting antenna, and then the object will reflect signal, and a receiving antenna on the radar will receive the reflected signal. The time difference between the transmission and the reception will be used to determine how far the object is located. Also, you can send the signal towards certain direction. You receive it from that direction, and that way you can determine which way or in which direction the object is located. So both the direction and the distance can be detected, and that's how you can actually determine the position in the 3D space. Okay. Well, whether the radar can detect the position in 3D space or just with 2D information, okay, classifies the radar. So it can be either 2D radar or 3D radar. Ours is a 2D radar. The one we have in our lab is a 2D radar. So the basic principle, you see that you send signal, okay, and you have a fighter plane that you wanna, some enemy plane is arriving, and your signal from the radar is sent, and then it comes back. Okay, so the total time is t tau out plus tau back. Now that from the total time, okay, you can determine the distance this way, that it is r by c, right? R by c, c is the velocity of the light. So your r will be like c into the round trip time, tau r divided by 2. Okay, so very easy to calculate. Like in this example, it is 150 tau. Okay, anyway, now you have actually everything changing in time. The fighter is changing its position, is flying. Okay. So you also need to update the information. You are determining a position, but you need to keep updating this position information. You need to show that now it is flying this way, here, then here, then here. Okay, you need to be able to trace which way it is flying, how the position is changing. From that, actually, you should also be able to calculate its velocity, its direction of flight, everything. So anyway, the point here is that you need to keep determining continuously. Okay, so this is why a pulse is sent usually. There is also an option to send some continuous wave. Okay, but more commonly, the radar has the variation, uses pulses, and then you call it pulsed. Okay, so these two types, another way to classify the radar. So you keep sending pulses one after another. So for this first pulse, you expect that the reflected signal, the reflected pulse will come back before you transmit the next pulse. Okay. Oh, sorry. It is the Is the transmit pulse is the receive pulse, but there will be uh, transmission of pulses one after another. So expect that the received pulse arrive before you transmit the next pulse. Okay, before the next pulse. So then you can determine the distance. Okay, I mean use this 200 microsecond as the round trip time to determine the distance. Well, there can be a problem which is called ambiguity. If the object is located too far, then the reflected pulse will arrive after you transmit the second pulse, and that is what is actually shown here. Like from this pulse, transmit one. Okay, this is the pulse number one. This pulse number one reflects and comes back here. Okay, but your radar will assume that it is a reflection from this second pulse. All pulses look alike. So it will actually use this 200 microsecond to calculate the distance. In fact, it is from this pulse, so you should have calculated using 600 microsecond. But you don't do that because it all looks the same. So in this case, what you need the period between the pulses should be adjusted. It should be longer. Okay, it should be longer than 600 microsecond. So the this is called pulse repetition interval, PRI, pulse repetition interval, and its reciprocal is pulse repetition frequency, PRF. So you need to set this value based on what is appropriate with the expected distance of the object. However, too large PRI has the problem. It's a trade-off, what you set for PRI. If your PRI is larger than required, then what happens? You actually update in every cycle. The information is updated in every cycle. So you update it less frequently. PRF tells you how many times you update the information in a second. So as you increase PRI, PRF goes lower. So you're updating, but the enemy plane may be flying too fast. And so you're updating less frequently. So you don't have enough information to trace the enemy plane. Okay. So now we'll go through the video captured. But here you see that this way, what we have discussed tells you the distance, but how you determine the direction? Well, you actually need to use a directional antenna. Ours is a 2D radar, so we only can determine the horizontal direction. The altitude we cannot determine. The altitude of the object we cannot determine. Okay, so think about the horizontal 2D radar. In this case, we have an antenna with narrow radiation pattern in the horizontal direction, and this antenna we keep rotating continuously. All of you actually know that for radar there's an antenna which keeps rotating, but this one has a wide angle vertically, so it can capture different objects over a wide range vertically, because it does not determine the altitude, height of the position of the object. Okay. So horizontally it has a narrow beam, so it keeps rotating. When you transmit in certain direction and you get some pulse back, then you know that there's an object in this direction, then change the direction. Okay, you keep rotating, and so you'll see the position of the objects in different directions. Okay. And I mean, the distance I mean, over a display, you show that in this direction you have, using some dots, you can show the positions. Okay. For the case of 3D radar, it is more complex. Actually, you may need the help of additional antenna, or I mean, scanning also in the vertical direction. Okay. And when you do that, then it's a 3D radar, okay, which gives information of both. And 2D radar gives you the distance. In the case of radar, the distance is called range, and azimuth, you know, is the angle from north, which way the object is located. And for 3D, it also gives you elevation information. Okay, what angle it is making from the direction of radar. And that's how, okay, this elevation information, or the angle it is making from the ground, actually gives you the height information. Questions? So this ambiguity is a problem which you need to overcome using proper setting of PRI. Questions? Okay. If not, then we'll move to the radar demonstration. We have a control panel, and that has this. I mean, here these are the buttons to turn the radar on. It takes initially 1.5 minutes to warm up. And thereafter, you can use this transmit button. Then the antenna starts rotating and keeps transmitting energy. This knob, okay, can be used to set the position of cursor here. Okay. And okay, now he's gonna press the transmit button, I think.
Sir, are you sharing your screen?
Oh, sorry. I'm so sorry. I started playing. Oh, man. Now you can see, right? Do you see the?
Yes, sir.
This is the control panel of our radar, and here's the display. Okay, and these are the two buttons to turn it on. First, press the standby button. Then it takes 1.5 minutes to warm up. Okay. Thereafter, you can press the transmit button. When you press that, the antenna starts rotating. I will show how it rotates, and the antenna also starts transmitting power. The knob here, okay, with different arrows in different directions, are used to change the position of a cursor here on the display. Okay, now he presses transmit. Okay, now you can see that it starts showing different dots, right? As soon as he presses transmit, it starts showing different dots. Well, these are in different directions you have different objects located, and energy is reflected from them. Okay. Now, unfortunately, what is happening here, you see the dots over a narrow angle only. Okay. So this is the problem we are facing this year. even last year. Well, the problems started like a couple of years ago. When we had, I mean, it keeps rotating and it keeps generating dots. When it completes one revolution, the antenna has completed its revolution. Okay, scanning in all different 360-degree horizontal directions. Then it goes for a second revolution horizontally. But I mean, the problem we started facing that in the second, I mean, we could see dots only in the first revolution. Okay. So this problem started like a couple of years ago. From the second revolution, we couldn't see the detected objects. Now this year, we have the new problem that it shows the detected objects only over this narrow angle. Thereafter, it stops working. We don't see any further dots. So I'm very sorry, but that's how we have this radar now. Okay, these are some controls like rain, sea. These are some controls. When you receive signals, there are a lot of also reflections from the raindrops. If it rains, then there can be some small reflected pulses, okay, with very low energy from rain. Or radar are, you know, almost invariably used in the sea. The ships use them. So when it is used in the sea, then the sea waves also reflect. So the small dots from there can confuse you. So there is a control here, how much you separate the small power levels compared to the power levels from different objects. You know that from some objects which you want to identify may also have the power levels small. Okay, so it is a trade-off. How well you how will you set the minimum level of power that you want to get displayed here? The minimum of, from the energy, different energy levels in the receiver antenna. What is the minimum power level that you want to get displayed here? Okay, so so there is a control here. So just make sure that you are not losing the desired objects, but you're not creating dots from the sea waves or rain. Okay, so for both rain and sea, there's control. So these are the objects here, the dots. So as I mean, this is this one is gain. Sorry, he was using just the gain. Okay, with gain you said the amplification. I previously spoke of C and gain, these two power knobs, but I didn't notice he was actually controlling the gain level. This is just an amplification. So as you allow higher gain, okay, at the amplifier, then you should have more dots. Okay, even power levels from small objects will have enough amplification, and they will appear on the display as dots. Okay, so with higher gain you have more dots on the screen. With lower gain you have less. Okay, then on the display it shows that okay, let me see. Okay, yeah, now it is showing the position of cursor. Okay, here you can have you have a cursor. Initially the cursor located at the center, but you can change the position of the cursor, and the position is shown here. The unit, you can say there are some options. You can set it in kilometer or mile or in nautical miles. You know, in the sea, people use, the Navy uses nautical miles, okay, which is little larger than our regular miles. So you can set the unit. So it is probably set to kilometer now. So the cursor position is 0.521 kilometer away from the center. Center is the position of your antenna. Actually, the radar antenna is considered to be at the center of this display. So the cursor is now at 0.521 kilometer away and 34, making a 34 degree angle. Okay. So you see, this is the position of cursor, and this is the position at the center. You have the antenna. So it is at 34 degree angle and 0.521 kilometer distance. So with this one, you can change the position of cursor. And then you'll see that here you see it is now at 19 degree 0.89 kilometer away. Okay. So changing the position. So using this cursor, when you think that there is a object that you are interested in, it may be fishy. Okay. So you can set the cursor position there and then determine where it is located, in which direction and how far. So like it is showing here 3.1 kilometer away and at 12 degree, making it an angle of 12 degree. By the way, this range, with this range, you can set the maximum distance, okay, of what it is observing. So it actually sets the PRI, okay, using larger PRI. I mean, there are other options to set PRI and all that, but basically when you have a longer range of detection, okay, then your PRI is longer. Okay. So you can set at the maximum, I believe our radar, I'll double check, but I believe the maximum range our radar supports is 90 kilometer. So even, I mean, we can detect, I mean, if you are doing something fishy, we can detect from our lab. Okay, so be careful from now. Even at
Sir,
90.
sir, can I ask?
Yeah, please.
Why is there no reading on the east and west side and the south?
Sorry.
This part is empty, sir. The east west. So
Oh.
the readings are mostly.
Okay, that is what I was saying, that it's a fault with the radar currently.
Okay,
we didn't have this fault even last year. Last year, at least in the first revolution, we could see all the dots in all different directions. Okay, so a couple of years ago, what the problem we started to get, that in the second or third revolution, the dots are not shown properly. But this time we are, okay, let me make it clear. This is the fault with the radar now. Currently we have this radar. I'm not sure if we can fix it. So in fact, if the radar worked properly, we would see dots in all different directions. The whole display would then be covered with dots. Okay, so but now because of the fault, it is not detecting the objects in other directions. Only over this narrow angle it is detecting. Okay, got it?
Yes, sir.
Okay. So we'll have two small other parts in the video capture.
Sir, can you upload this video separately?
I have already done it. Just
Oh.
I mean, one of these parts are not yet uploaded. That I will do after this class.
Okay, sir.
The rest are already uploaded. Now you see the radar antenna. It is rotating. So
could you share your screen?
Oh, man, I'm so forgetful. I can see, right? The antenna. Can you see something rotating? Guys, do you see?
Yes, sir.
Okay.
Yes, sir.
So this is the radar antenna, and you see that it's actually an array antenna with microstrip patches. Okay. See, it is flat and it has just a layer of substrate on which you have metallic patches. And they all together form an array. Now, which way it is wide, horizontally or vertically? The whole array antenna. Consider the whole array antenna. Which way the antenna?
Horizontally.
Horizontally, it is wide. Okay. Vertically, it is very narrow. Now, can you suggest me how the radiation pattern would be out of this antenna, horizontally and vertically? I mean, just make the comment in terms of width. What's your expectation?
স্যার ওয়ালে স্যার যে সাইডে ওয়াল আছে স্যার ওখান থেকে আপনার রিফ্লেকশনটা বেশি আসবে
No, I'm just talking about the radiation pattern, expected radiation pattern of this out of this antenna. See, walls don't reflect much energy. You get, well, to some extent walls do. I mean, especially the large walls, of course they do. But you get more energy back from metallic objects. Okay. I mean, of course, large buildings reflect enough energy. You detect them too. But when you have metallic objects, then you get significant energy reflected. Okay. Radars can more precisely detect the metallic objects or that you actually have to use on aircraft. Stealth aircraft are there. Stealth aircrafts use, say, some. They use two different techniques. Some material which absorbs energy more. Okay, let me tell you, only a few countries possess stealth aircraft. Its manufacturing, its design is very difficult, and its manufacturing is even more difficult. Okay, so only the major countries like China, USA, France, Russia have aircraft, and I UK. Okay, I think that is pretty much the complete list of countries which have stealth aircraft. Okay, so anyway, so in this, the stealth aircraft diffuses the energy in different direction. First of all, they use some coating of materials which absorb energy, so they reflect less. Secondly, it deflects the energy in different directions. So that requires some, previously they used some flat shapes, pieces of flat shapes on the body of the aircraft. Currently, they use smarter versions where you have some round shapes. Now, the challenge is that when you want to use some shapes which deflect energy in different directions, okay, not in certain directions, so the receiver antenna don't get sufficient energy. When you use this type of shape on the body of the aircraft, it is no longer conducive to flying. Okay, you have at the same time, you have requirement of a design for flight, right? The aircraft has to fly in a very challenging environment too. So the stealth aircraft to hide itself uses a shape which is not. I mean, the requirements are just opposite. Okay, so that poses the challenge, and you have to be very precise. Yeah.
Can
Okay,
we
now,
just increase the power to detect those stealth aircraft? I mean, the radiation power of the antenna.
well, yeah, receiving antenna is more sensitive. Okay, but I mean, it's the quality of the stealth aircraft. Okay, how much it is able to hide itself. And you know, when Osama bin Laden was killed, USA sent 4 aircrafts. Just one of them was shot down there. by actually the people of Osama bin Laden. But Pakistan army raiders, okay, Pakistan defense could not detect any of them. And USA was sure of it. USA knew very well that they would not be able to detect any of the aircraft. So just furtively, they made a successful mission. All the aircrafts went there, killed Osama bin Laden. And 3 of them shot down from the, someone went to the roof and just shot an aircraft. But with the rest 3, they came back. Okay. So anyway, now the radiation pattern would be, you see it is wide horizontally. So the radiation pattern would be narrow horizontally, because we know that you need a large design of antenna to generate narrow pattern, radiation pattern, right? Vertically, it is small in width. So the radiation pattern would be large in width. You will have wide radiation pattern. So vertically, you can detect objects in many different directions, but horizontally it is narrow. So you can detect the direction of the object. As it rotates, horizontally have a narrow radiation pattern. In a particular direction, you're sending your signal and you get the signal back. You know that the object is located in this direction. It moves to another direction with narrow patterns, so you know there may be something or not. Okay, so at different directions, horizontally have some narrow, some small granularity in terms of directions. Okay, so it makes sense now why it is wide. If you look at other radars in operation in our AR pattern or something, okay, 2D radars will always have, most radars you will see like this. Horizontally it is wide, vertically it is narrow. Okay, there's some additional devices to when you implement 3D antenna. With a cover on top of it, which has been removed for the purpose of demonstration. You see, you need to feed with different phase. The different elements in the array. Okay, just another small presentation similar. Do you see the video?
Yes, sir.
So I think this one does not contain any additional information. It's sort of repetition, but he's now turning off the radar. In the case of our radar, we just have to, when you turn off, we just have to simultaneously press both these red buttons.
Sir, what could be these objects in the radar? The buildings or?
Yeah, well, it can be even, there are some misdetections, even sometimes, these are called false detections. And sometimes large birds are even detected. Okay, and there are some measures like you send some missiles or something to protect yourselves, and so you so there are sometimes false detections. So even large birds sometimes confuse and they launch some missiles or something to towards the bird, but most of the time they detect properly. Whenever there is something really enemy object they detect. But the point is here, anything that can give you sufficient signal back will appear as dots, like large buildings. Okay, but if you consider some rough surface, something that scatters, then you don't get enough energy back. But when you have good reflection, okay, then you'll have significant energy back. And if it is metallic surface, then of course you have a lot more better, you have a lot better reflection. Okay, so even if it is not metallic, you can have significant energy back, but the surface then should be smooth. Okay, so the smoothness, the type of material, the shape of the object, all these things matter. Okay, I think we can. Do you have any questions?
Sir, what is the purpose of that rain and sea switches?
Well, there are some small reflections when you use the radar in the sea. Okay, so on the ships, almost invariably you have. So the sea waves also reflect small energies, and the receiving antenna get small energy levels from there too. But you don't want to see a lot of dots out of your sea waves, right? So your whole display will get blurred with the sea waves. But you also want to make sure that you don't miss your desired objects. Oftentimes the energy level from your desired objects may not be enough high. So there is a knob to control how much minimum energy you want to see on the display. Okay, so that you can separate, you don't get confused with the sea wave dots. Also, you don't miss any desired object. Similarly, from raindrops, you can have a lot of small reflected energies back. So just to separate from these unwanted dots, okay, there is a control knob. Any other question?
Sir,
yes.
Sir, for the analyzer, what waves do you use for testing?
You can capture any signal, say the signal in the air. Like if you hold what we used to do, we used to hold a mobile phone, okay, and set the frequency span over the band that we use in our country, okay, for cellular operation. Then when you make a call, it transmits good level of energy. In the next semester, actually, we will explain how it sends the power level when you start making a call. Okay, the power levels can be sufficiently high then, and it can be gradually even increased. So you'll see some spikes then within the band. We used to show it to the students. Okay, on the display, when you just make a call, you see some spikes. So you transmit good level of energy. Okay. Also, you can connect a cable, coaxial cable. You have from some other circuit. You generate energy. Okay. The EM wave you can feed to the spectrum analyzer. Anything else?
So any suggestions regarding the lab quiz or when it will be
Yeah,
held or how it will be? Yes, sir.
yeah, we will discuss. There will be a written quiz, but let me talk to other teachers in this lab course, and then we'll talk about our assessment procedure. Okay.
Okay, sir.
Okay. So we have a theory class, makeup theory class tonight at 7:30.
Okay.
So I'll meet you then.
Thank you, sir. Assalamu alaikum.
Wa alaikum assalam.